Hi, everyone. We've set up this Being an Engineer podcast as an industry knowledge repository, if you will. We hope it'll be a tool where engineers can learn about and connect with other companies, technologies, people, resources, and opportunities. So make some connections and enjoy the show.
And then here's the problem. We're going to solve the same problem again. I guarantee I'm going to see the same problems being talked about and solved that guy Ralph a year ago had already done this work. And he was a good engineer.
Hello and welcome to another episode of the Being an Engineer podcast. Today we are here in the studio with Shawn Patterson, who has developed an expertise in process development for electro-optical and mechanical engineering platforms. Shawn has taken prototype engineering efforts and carefully improved upon aspects of their thermal management, method of assembly, and package design. Shawn, thanks so much for joining us today.
Hello, I'm very glad to be here.
All right, so can you tell us a little bit about your background?
Yes, I started my laser career in outside of Boston, Massachusetts, at a company that was designing the very first LASIK machine. And this is before they were FDA approved in the US. So about 1996, I started working there as a CAD drafter. And the engineers took a liking to me, and I knew not much about engineering and certainly nothing about lasers. But I never did much CAD drafting there, and I got pulled into the labs for laser testing. And do you want to know what a laser is? Do you want to see they would entice me to come in the labs. They took a real interest in me, and I ate it up. I was in my early 20s to mid 20s. So I got involved in lasers that way, and I excelled at that company. And best friend of mine was at Northeastern University for engineering himself, and he was interning there. And we were working on FDA approval and getting ISO approval and moving through all the steps to be ready to sell lasers that would correct vision. And I did a lot of interesting projects there, and it stamped engineering in my DNA.
Okay, so Shawn, you didn't just jump into engineering right away. Tell us a little bit about that journey, right? You mentioned to me before we started the recording that you kind of took some time to explore a little bit and figure out like what's out there and what are you really going to enjoy? Absolutely.
If I had chosen to go to university at 18 out of high school, I'm sure I would have chosen wrong. I didn't know anything about engineering at the time, but I was mechanically inclined. But I left, home around the age of 18 or a little earlier. And I moved to Santa Barbara with my girlfriend. And then I hung out there, like figuring out what I wanted to do and meeting friends and, learning to surf and everything you do in Santa Barbara, really enjoying it. I was there to have fun, but I was also cognizant of I'm here to gather intelligence to help me get to a career in life, and I didn't know what I wanted. So living there, I took some CAD classes when Autodesk was making AutoCAD, and this is before SolidWorks, many decades before SolidWorks. But in any case, I took architecture, so I was drawing residential architecture and building architecture at the City College, Santa Barbara City College. So I did that, and then I had an opportunity to go to Boston and sell all my stuff and just go. And I had not built a family yet. I had no wife or children. So I sold all my stuff and I did that.
Nice. What a great adventure.
Oh, I was out for adventure for sure. So
you mentioned, I think it was at Boston where you first started learning about lasers. Some of the engineers there kind of took a liking to you and started introducing you to different technologies and things that they were working on. What do you think it was about you that encouraged them or made them feel comfortable pulling you in and wanting to share some of their work with you?
I think it may have been my youth and my California-ism because they were on the East Coast and they thought I was the cool guy. That I was a California kid.
Ah,
and this
okay.
is, the early 90s to mid 90s. And they probably, I think they hadn't even been to California. So I was just like this kind of cartoon character from California almost. And do you surf? And oh man, in Boston, not many people surf, even though they're on the water, but it's just the wrong kind of beach. Yeah. So in any case, they took a liking to me. They found me to be a cool guy. I was, I don't know what I had, maybe a cool factor or something. But anyway, these guys were family men and older engineers. I was out for an exciting time, and we all really meshed really, really well personality-wise, even though they were from the East Coast, and I had never been to the East Coast, so I was just learning about the Boston attitude, accent. They're different than Californians, and Californians can be lackadaisical, and Bostonians, they keep relationships a long time, and when they say they're going to show up, they show up. And they, you become someone's friend in that area. You're like a friend for life. So we went river rafting in Maine. They invited me. I was stunned. And at this company called Summit Technology in Waltham, Massachusetts, it was just, my first engineering job. And I couldn't believe it when I saw my printout of my work statement said that I was in the R&D department. I worked in R&D. Wow. How cool. I work in R&D at a corporate company. It was a startup, but it was a funded one, well funded, I believe. And a lot of things were defining me at that time. And I had been looking for definition. So I was running with it.
That's awesome. So you got into lasers and optics, and that's kind of been a theme throughout your career. Give us a sense for how do engineering teams use optics professionals like you? Like, what are some of the problems that you have solved or that you could solve? Because I think a lot of engineering teams have not worked with any optics personnel, and so how do we work together? What do you do?
Well, I luckily stumbled into optics and laser systems in Tucson, Arizona. I did it there when I came out west to get an engineering degree. And so I did 3 years of an optical sciences and BS at U of A, University of Arizona in Tucson, and
which is known for optics
Valley, and yes, strong optics program. And in any case, I did 3 years of that degree, and then I fell into lasers. I fell out of school and into a startup engineering laser company called 4D Technology, and they were making a new type of interferometer, which an interferometer is a metrology device that measures high technology surfaces, can measure ICs, integrated chips, silicone wafers, telescope mirrors. It gives you the topology down to nanometer levels. And it uses the laser to do that, and optics and a whole optic train and polarization of the laser and all these qualities. But I was leveraged for my persistence, my creativity, kind of my free spirit, I think, because I had to do some weird stuff there. I had to interpret a lot of weird things with these. When I say they were approaching this metrology device in a new way, I mean, it had been done temporal. So with time, they were doing it spatial, meaning time didn't matter. And with these delicate instruments, very sensitive to vibration, if you need to take, 12, 15 microseconds to take a measurement, you can get vibration introduced into the measurement, which lowers the resolution. But if you can take it all instantly, you can take it on a vibrating table. So they had developed and really mastered a way to mask the CCD cameras that were taking the images. Pixel for pixel, they would put polarizers. And so every block of 4 pixels became a superpixel, and it had the different angles of polarization to add up to 360. So 90, 120, 180, 360, all the way around. So instead of moving the test piece with respect to the reference, you could leave them steady and not have to wait for it to move forward or move back, but they could be steady, and the information would be caught in the superpixels because it turned the polarization of the light. So it accomplished the turning of the 2 pi theta turn instantaneously. So you had lower resolution than a megapixel camera, because it was a megapixel camera, but divide by 4, and that's how many pixels you really had.
Yeah.
But then, of course, we bought a 4 megapixel camera, so we could have a 1 megapixel image. But getting those to line up, and there's more fringe patterns, and there's gluing that mask on the CCD and getting it to be a sellable product was very challenging, and I was one of the few people that could do it.
Wow. Okay, so this gets into another question I have, which is, what are some of the tools that you use as an optical engineer? And even, are there some basic optics tools that engineering teams out there who maybe dabble in optics every now and then might want to consider adding to their arsenal?
Then in optical sciences, it depends on what you care about, what you're looking for. If you're looking for beam quality, you're going to use, energy detectors, and you're going to use setups with XYZ stages, and mechanical engineering plays very heavily in laser science. And there are spectrum analyzers if you care about the wavelength. If you care about how concise the wavelength is, or how narrow your spread of wavelengths is in a laser, because people will tell you that a laser has a single wavelength and that's what makes it a laser. It's coherent, it's one wavelength. It's rarely one wavelength unless it's a very, very expensive laser, because there's a little spread of frequencies there that are, if it's a green laser, there will be just a bunch of green frequencies, and it's still a laser, but it has a spread of wavelengths. It has a line width. If you look at it on a graph, it's not just exactly 532 nanometers like anything. So, but the lasers. So if you care about wavelength, or you care about wavelength spread, or you care about beam quality, there's a lot of beautiful things to see in laser science. I mean, you work with crystals when you make solid state lasers that we pump and energize crystals, and the crystals will take a certain wavelength and then double it or half it. And now you go from the invisible regime to the visible. So now you've just taken infrared and made it bright green. And with these crystals, and they are doped with impurities, to get this behavior out of them. The way a laser based on solid state crystals works is fascinating.
So let's get into like the basics of a laser.
Okay.
What is a laser, and what are the core components of it? How does it work? And this could quickly go over, I think, most of our heads. So try and keep it kind of basic.
Yeah, it's pumping electrons with energy to excite them and getting them to an excited state. And they have orbitals that it's like stair steps. It can only be on one step or the other. There's no in between. So you energize. So you have to put energy into a laser cavity to energize the lasing medium. And these electrons, valence electrons, will jump up to higher energy states. And then the correct photon will come by, and it will stimulate a drop in energy of the electron. And that drop, the delta of energy there, you've just lost some energy. Well, it doesn't go nowhere. It turns into a photon that matches that introductory photon. Now you have two. This happening, billions to trillions of times inside of a laser cavity with many atoms and electrons. You get a cascading effect, and you get what we all love this word, gain. So you get laser gain, and then you get lasing, and you have lasing action, where now your cavity is bouncing between the two mirrors that terminate the cavity, one will be an output coupler where you will get the output, of course. And then the other is a high reflector. So between your output coupler and high reflector, you keep the energy inside until the gain is high enough and you're pumping it with electricity. And so there's an electrical to optical efficiency. You're going to put in more electricity than wattage that you're going to get out, of course. But what happens, some of it goes in heat, and then, it's this conversion that's happening. You exceed the output coupler when you finally get enough gain. Now you have a laser beam leaving the cavity. And now you work with that. What's your energy distribution? Are you Gaussian, which means nice and warm in the middle and cooler on the outside if you're looking at it radially, like a cross section? And that's you're not going to get that at first. You're going to get wobbly, looking beams, and then you got these different modes inside of a laser that will take over, and it will want to do this on this mode, which is maybe if you were looking for 532 nanometer wavelength, you might get 540 that wants to laze, but that won't laze as efficiently as 532. If you can get it down to 532, and you got to use temperature, thermal dynamics, crystal placement, alignment is super duper important in these lasers. And the ones I was making were tiny, like a pinto bean. Okay, so I'm using pick and place machines that, can place these tiny 1 millimeter cubed crystals, or maybe 1 millimeter, squared by, and then it's longer. So a longer, maybe 5 millimeters long, 6 millimeters long, these different crystals, and then a very tiny diode pump, which is the initial energy input. You pump these crystals, they do their magic, you get laser output.
Wow. I don't think I've ever actually heard an explanation of what a laser is, or if I have, it's been a long, long time. All right, this is maybe a silly question, and it might open up a whole can of worms here. Why don't we have really cool laser guns like in Star Wars? What's preventing us from getting there?
Laser guns.
Yes.
We have lasers, and they can be in the form of a gun. I mean, you can point a laser across the parking lot and burn a hole in the side of a car with a hot IR laser, infrared laser, 1,000 nanometer wavelength, or somewhere in there before you get to far IR, because then the frequency is kind of lazier and slower, how fast it's oscillating.
So why don't we have it in like a hip holstered gun, like in Star Wars? Is there there's not enough energy density in our?
I see. It you could have that, and it exists. I mean, I don't think people want to carry that around, like you carry around a firearm, but
Too
equally
many
dangerous
to yourself, maybe.
Yeah, it's it would be pretty dangerous. And you could make one that pulsed, so it would send a pulse like a bullet is a single projectile. You could send a single pulse, so it's loaded with energy, and then pulse, again and again like a machine gun. I'm sure that exists. I go on YouTube, I see people burning their skin with blue lasers, or popping balloons, or lighting things on fire with lasers. Blue is a very high frequency, and the last high frequency you can really see with your eyes. Then you get to violet and ultraviolet. But those high frequencies have a lot of energy, and the red will have less energy, and the infrared will have even less energy than that. But here's the thing about lasers. A watt laser output of a watt, a joule, a watt, that is much more powerful than a light bulb. When you think of watts of a light bulb, no one buys a 1 watt light bulb because you can't see anything with it, hardly. But a 1 watt laser will burn through your leather couch, and if you focus the beam or not, you'll get even more power density.
Yeah.
But, lasers dissipate in air. They start, if you send a collimated beam, because I at the U of A, we made tripods, and we had lasers on top of buildings going from building to building across the campus for experimental stuff. I was in the optical sciences program. We'd be up there at night with red lasers and pointing to a receiver across campus and trying to make sure we could hit it and these types of things. And we could collimator beam, but by the time it got there, it had spread out quite a bit. And so the energy density is less, right? And so it's hard to keep that on a long distance. And the solution is not to focus the beam a little bit and think that it's going to spread less. It kind of doesn't really work that well. But smaller, tight beams, and this is where beam quality comes into play. So as I said, what were you looking for? You're looking for wavelength adherence or beam quality, or, for the tools you want to use in your lab, you need a spectrum analyzer because you want to know the spectrum of wavelengths. Some lasers can put out 2 wavelengths, and I've seen that in fiber optic lasers. Raman laser can put out, yellow and green at the same time. But in any case, these lasers as weapons are probably best left in the military's hands.
I'm sure the military has done deep research into how lasers can be weaponized. And the fact that we don't have laser guns like Star Wars probably says that there's got to be some kind of physics-based limitation, right? Or maybe a normal bullet gun is just every bit as good as a laser gun. So why spend the money to develop a laser gun? I don't know.
Yeah, there's I think there's a laser system that keeps track of how far away the moon is.
Okay, so that's a perfect segue into this next question, which is a lot of people, when they hear lasers, they might think about cutting or burning with lasers. Of course, there are far more uses for lasers than cutting or burning. What are some of the other uses that lasers are commonly used for?
I can tell you one that's pretty interesting is the crystals I mentioned earlier. They get hot, and you don't want to have an active cooling system if you can avoid it. You would like them to be passively cooled. So you need a heat circuit. Well, lasers can be used to metallize the bottom of a dielectric or a surface on a dielectric crystal to metallize it. Usually gold will be the choice of metal, but then you will use a laser to adhere this metal to one surface of the crystal, and it would be the bottom surface, so that you can weld it or solder it to a metal base. Now you're going to have a heat circuit. You're on your way to controlling or managing your thermal, increases and stuff. So lasers can metallize dielectrics, and then you can solder them to things.
Very cool. All right. Well, let me take a brief break here and share with the listeners that teampipeline.us is where you can learn more about how we develop or help medical device and other product engineering or manufacturing teams develop turnkey equipment, custom fixtures, and automated machines to characterize, inspect, assemble, manufacture, and perform verification testing on your devices. And we're speaking with Shawn Patterson today. Shawn, what are a couple of the biggest failures that you've had in your career, and what have you learned from those experiences?
It's a good question. I'll go back kind of in school at University of Arizona. I struggled a lot with the speed of which 400 years of engineering and science is being thrown at you. I struggled with wanting to slow down and absorb it instead of week to week, we're on to the next. This electromagnetics and physics of this type and physics of another type and differential equations and high math and Calc 4, and I don't even remember Calc 1. Still my identities and just going so fast. And I had a more romantic view of what getting a degree would be like. And I wanted to know about the scientists themselves. I mean, I read about Ampere and Volta and these scientists that developed, so many of the rules we use, Maxwell. And in any case, so it wasn't like that. So I really struggled there. But, I, as we all have done, or people who've tried to get an engineering degree, it can be tough, and you're up late at night and you're pulling your hair out and you're sweating for the tests and you're wondering if you know everything, and you shouldn't be studying up to the last minute because that means you're not prepared, but you're going in and you only got you to count on yourself and you do your best, and sometimes you get enlightening moments during the test, and Some of my tests were 3 hours long, and 3 to 4, maybe. So in any case, I struggled at university, but I also learned a lot. And one of the things I learned is that learning calculus and these types of mathematics are not so you can then be an engineer some years later and pull out paper at your desk and say, oh, I'm going to write this integral. I got a problem. I'm going to fix it here. I'll just put it in an integral and solve this line integral. Oh, there we go. 4.7 feet. Great. That's what does it. You don't do that. Why you learn this math, or why I think I learned it, was to help you think analytically. It taught me how to think about things and how to just delve deep into it and get into. So I struggled there, and then I had been trusted a lot at a company I worked for, ADE Phase Shift, which I think was just called Phase Shift at the time, but this was in Tucson, and I was entrusted with building the new 12-inch aperture, which was very large for this machine that used to be 4-inch aperture. We were making a gorilla-sized version of this great interferometer that was called a Fizeau, after the scientist Fizeau. And it was an interferometer inside it. There were nested 3 interferometers to kind of build up that beam path to get to the output that was 3 times larger diameter beam coming out to measure big surfaces, large telescope mirrors and things. So I was entrusted with building it, and I did my best for several weeks, and I really felt great about the trust they put in me. And when I finished it, and to me it was perfect, and I dotted all my I's and crossed my T's, in quality testing, it came out that my beam quality was bad and giving bad results, and the software was not interpreting the maps right, and I had misaligned it somewhere. And in lasers, the next word you're ever always going to say is alignment. Laser systems, alignment. It can improve efficiency. It can polarization and alignment together. You're working with these things to really pass through all the doors in the optical system cleanly and then get your output that you want. So I had fouled up in the alignment, and it was the first off. So, and I was a lone wolf on this project, and I love that they let me do that, but it failed through final test, and it was still 90% there, but they sent an engineer in to fix it, and no one said anything to me. And it really felt weird. I felt like an outcast, and I kind of, in a roundabout way, I found out that he was sent in to fix my work, and he fixed it, and then it went out to probably NASA or somebody, a very important customer. And no one ever talked to me about it, and it was just strange. Life goes on, but I felt a little downtrodden about that, or, crestfallen in that I was really had built a reputation, and I was my reputation for what I could do there. And I wanted to impress the leader of that company, who was Chris Koleopoulos, and he was a professor at the U of A, and then as he told me, he got tired of seeing his students go off and start businesses in optical sciences and make more money than he did as a professor. So he said he started phase shift technology in Tucson, and this guy was a maverick, and a really strong one at that. I mean, he is really a great leader. And anyway, I knew him personally, and it was a small company, so you could know the top, very easily. And I felt like I let him down.
Well, thank you for sharing such a personal story. How, you mentioned that it felt like maybe they kind of circumvented you.
Right.
How would, if you had a chance to go back and kind of relive that time, what would you have said, or how would you have requested leadership to handle that situation? Because I imagine there are engineering leaders listening right now to this episode who maybe are dealing with similar situations, and maybe they don't know the best way to handle it. So how would you have preferred that situation be handled?
I just would have liked to have been included in the the failure analysis, the FA. I would have really liked to have been included in that. I would like to have been shown the bad maps it was making. I would have liked to have been held accountable, but I wasn't. I wanted to be held accountable, and therefore, or ergo, learning, right? But it wasn't handled that way.
Yeah. Have you had any opportunities in your career since then where maybe you were on the other end, right? And maybe you were like supervising or coaching someone else, and you had the opportunity to like correct some other engineers or technicians' mistakes and help them learn like what's the right way to do this?
Yeah, I have. I've had to bring people and show them their mistakes before, and people with more degrees that I don't have, and engineers further along in their career. Everyone can create a mistake and do something wrong, and sometimes it doesn't matter who digs up the root cause.
Yeah,
the root cause. But I have, and I think it's it's not easy to tell someone, they made this mistake and come look at what you did. And then it depends on the personality, because they can have excuses right away, or they can be all ears, and they want to know what they did wrong, and they can let you just be the authority and show them this happened. I found this, and you forgot this, and we need it. And you can't go to the point. It's work, so I can't go to the point of why did you forget that? It's almost like asking, are you here? Are you paying attention to your job? You got to broach it, in these certain kind of ways.
Sure. Yeah. Well, I love that you used the phrase, I wanted to be held accountable. That is such a great attribute of strong engineers, right? We don't want to be let off the hook necessarily. We want to learn from our mistakes, and that's a really important behavior. Along those same lines, based on your experience, past 20 years, whatever, how have you seen engineering teams mess up product development? What are some of the common mistakes or problems that we make as engineers?
I would say one thing would be exit interviews. So when people leave the team and there's no one in charge of retrieving their lab books, their computer directories, their paper in their office, their posters, their everything, and compiling it back into the rest of the people that are still here. Hey, Jim, do you need these graphs? Because, Ralph left and he made a bunch of this. He did a bunch of work here. I've not seen that done very much at all. And I've never seen anyone in charge of that. And then the lab books get left. Somebody cleans out the cubicle. The next guy comes in, and I don't know where the lab books go. And then they may be given to someone, and someone puts them in a drawer somewhere. And then here's the problem. We're going to solve the same problem again now that Ralph already solved. I guarantee I'm going to see the same problems being talked about and solved that guy Ralph a year ago had already done this work. And he was a good engineer.
I couldn't agree with you more. I'm going to do a little plug right now for something that we've been working on. It's a platform of tools, education, and community for engineers. And the whole idea behind this whole thing is we've had hundreds and hundreds of years in engineering to figure out the wheel, yet we continually reinvent it as engineers. And I think that's a source of frustration for so many of us. Chances are what you're working on, someone else has worked on something very similar, if not identical to that. Some company, some time period, somewhere, someone has probably done something very similar. So why can't we pull all that information into a single repository where it's easy to find and stop reinventing the wheel? All right, so that's my diatribe. I'm done off my soapbox now. But anyway, I agree just so much with what you said there. What skills do you think the best engineers have?
Don't panic.
Okay.
I've had bosses and higher ups that do that, and it's never, productive, or it doesn't add anything good. And I've had to deliver really bad news to my bosses sometimes, and sometimes late at night before customers are coming to see if they're going to buy our startup. Like Texas Instruments TI was coming to buy our green laser program at Compound Photonics, and that would have really been great for us because we were seeing some investor fatigue as a startup, and we had been several years into the game and not made a profit. We were pre-revenue, as they say. And the night before they're coming, the big wigs are coming, and two of my laser demos down in the lab are not working. They stopped working all of a sudden, and they were the most impressive ones that would have really maybe tipped the scale in our favor. And I have to go up to my boss and give him this really bad news that I've troubleshot it 6 ways to Sunday, and I can't get this thing to work. And we're out of diodes, or we only have 3 other good ones, and we're scrambling. And can I take that crystal off of that other laser and weld it to this one tonight at 10 p.m. to make it work? And I don't even know if that's really a surefire fix. So in any case, this man, I'm giving him the worst news that I can give him, and he's saying, okay, what temperature were you running at? What are the amps? Did you save the data? Which oscilloscope are you using? Let's go downstairs. And it was a downstairs lab. So let's go down and take a look. That was his approach, not, holy, expletive, this expletive, that. And this is a company killing prospect. And what the hell are we going to do? And how did this happen? And damn it, this. And then storming down to the lab. No, this guy, I won't say his name, but he was one of my best mentors and bosses.
That's amazing. Well, speaking of tough projects, what are 1 or 2 of the most challenging projects that you've worked on?
Challenging. Working with water systems can be really challenging, and water cooling lasers that are going to go in the field. I worked on, at NP Photonics in Tucson, I worked on a laser system that would be drug along the ocean floor in the North Atlantic to look for oil. So these are fiber optic lasers, and there's some 64 of them in a box, and they're going to have all their tentacles down fiber optics, and they're going to be drugged by this enormous, oil hunting ship in Norway or somewhere in the North Atlantic Ocean. And this system had to go underwater, but it had to be water cooled, and the lasers had to be, all these lasers together had to work in sync. And this was one of the times where a salesman overpromised in order to get us a sale, and came back with this really wild idea. And our engineers worked on it, modeled it ASAP, kind of running fast, working nights and weekends to put together this ocean floor investigating laser system. And I was new to electronics in a sense, and I really realized I had to really hunker down on soldering and test. And soldering is not trivial at all. Soldering is very important, and doing it right is very important. And the same physics that come up with anything is, as far as thermodynamics and things, are really important in good solder joints. And all of these things, when one solder joint fails, you're done. I don't want to poo-poo anyone, but a lot of graduated laser engineers do not know how to solder anything, and they're horrible at it.
Raising my hand here.
Okay. So I've taught engineering groups of engineers how to solder and how to correctly splice wires and how to make good solder joints and all of this stuff and methods and things like that. But in any case, we were doing a new project, and our company was, really, it adds to the excitement and the impending peril of if we don't get this money, and sell this project and get it there on time, and it's got to work when it gets there, and it doesn't even if it works when it's here, to say it's going to work when it's there, it was the first one we built. We didn't have any prototypes of this. We're sending them the prototype and kind of acting like this is a product. A prototype is not a product, okay? You don't go to Best Buy and pull electronics off the shelves that are prototypes to take to your house. So in any case, a very challenging project and time intensive, and a lot of new technology and software, test systems, failing lasers, fiber optics, temperature controls, stopping water leaks. Just water's a crazy, when you're trying to contain it and tell it what to do, water pushes back.
Probably like the understatement of the year. Water pushes back.
Yes.
All right. Well, what's a tool that doesn't exist, but if it did, would dramatically accelerate the speed with which new products can be developed? And this can be outside the realms of what's physically capable, or at least what engineering and science know to be physically capable.
Yeah. We are everyone probably says this, but we are in a modern age of toolage and software programs and modeling capabilities. Today, 3D printing has enabled geometries that you just can't do with a lathe or a CNC. I mean, you can't CNC a sphere that's hollow in the middle with a lathe. You have to make two halves, but you can 3D print that. So in any case, we have a lot of tools. We have a lot of modeling, FMEA and stuff. So we have a lot at our fingertips. But if I was, a tool, my headaches have always been rooted in failure analysis, FA, and root cause. So I would ask for a magic machine that could scan a system like Star Trek and find out which tiniest little component in a circuit is failing and why, and fix it.
There you go. All right.
And be certain.
We've brought up Star Wars and Star Trek now, so I think our work is done in this engineering podcast.
Okay, right on.
All the basics have been discussed. Right. Actually, I do have a couple more questions before we wrap this up. The first one is, if you could write a short sentence or a phrase on a billboard that every engineer in the world would see, what would that be?
What comes to mind is a sticker I used to have on I had a chart in my cubicle of the electromagnetic spectrum from cosmic rays to radio waves. And the sticker said 186,000 miles per second. It's not just a good idea, it's the law.
Physics is a thing.
Yes, sir. So that's not an original thought of mine, but there was also a woman that used to wear a shirt and it said on the front, it just said, "Get automated."
I like it. Hey, that sounds like a plug for Pipeline. Get automated. I love it.
Absolutely.
All right. Well, so specifically within the context of your role as an engineer, what is something that brings you joy, and conversely, something that frustrates you? I guess you already talked about failure analysis, but maybe there's another one out there.
There is. I've worked with people that when we have some piece of equipment that we don't even understand, maybe we bought a new spectrum analyzer, or even it could be simpler than that, a chiller of some kind that has menus and a computer and a brain, and you have to figure out how to make it do this and that. People that just start pushing buttons. People that just start going through the menus and changing stuff. And then
without
they
knowing
back
what they're
out,
doing, really.
and they don't know what they're doing. And I'm like, whoa. And I'm holding the manual, right? I want to, so that kind of thing. People that don't respect very expensive lab equipment, and they just go smashing their fingers into the buttons, but also just any of the adjusters. I don't like when people just run their palm on a micrometer instead of using your fingers to turn it like a human being, but like ramming your paw on it to spin the handle that's knurled so right. You can grab it with your fingers, but they want to get there faster this way.
Yeah.
And this motion, and I'm like, oh boy, I need to either leave or do, I don't know.
I can see that grating on you mentally, just thinking about it.
Yeah. Yeah, I'm already not feeling great about this now. Just kidding, but
Beads of sweater coming off your forehead here.
right, because I've never been anyone's direct boss. So I have to ask them, please don't do that. Please do it the right way. You don't say something like do it the right way. See, you have to keep relationships at work.
Yeah.
You can't do it like you yell at your little brother.
Okay, so how about the opposite? Something that brings you joy as an engineer?
Brings me joy as an engineer is presenting great data in a meeting and a review, like a design review, to people that were not involved in my project, but they were all going to share. And like everyone wants to know, how's that project going, Shawn? We're going to, the meeting you're going to present, and I prepare my PowerPoint and I show up and I have good data to present. And I have a style that I work, I take great photographs with my phone when I'm in the lab, and I'll edit the photographs and put the arrows where they go and show, glowing crystals that are making a laser beam output, and I love putting together really good presentations, and I love presenting.
Another thing we talked about a little bit before the show is that you are also a musician, singer, songwriter, and has being a musician helped you with presenting as an engineer?
Maybe so. I've been doing open mic nights around Phoenix for a couple of years now, and that puts you up in front of people and talking. And it might, because performing, that's just another way of performing, playing music for people or presenting, quite different, but still performing is there. I'm not sure, but this is something more that the confidence in presenting had to grow with my seasoning in engineering and knowing what I'm talking about after more years that I have experience in this profession. So I wasn't always like that. So that's what I'm getting at. Yeah. So my confidence level rose, and then I've had some really great, at Compound Photonics, I really conducted some great projects to very successful ends in unknown environment space that I was working in, and can it be done very well? And then meaning that then after my lone wolf period in the lab and reaching out when I need help, when things I don't know, I need some wire bonding done, I need some gold wire bonds, I need something redone, measured, whatever, people help you, but then I'm on critical path, right? And that carrying that through is just really exciting and really rewarding and fulfilling, and you get this great sense of, I earned my money today.
That's a good feeling.
For sure.
Well, is there anything else that we haven't talked about that you think listeners ought to know about your experience, your insights into the industry? Anything else that comes to mind?
Yeah, just have a free, open mind about it, and be determined to look deeply into your projects and your interest level. Sometimes you have to artificially make it high because you may not love your project sometimes, but learn how to really get your focus and reach out for help when you need it. But just thinking, stopping to think is really important. You will come up with ideas that you didn't know you had when you think about it, but you have to have some understanding of it to be able to think about it. Back to calculus and things like that. That teaches students how to think. It's not that you're going to be writing derivations on your desk, because you're not. You don't do that after you leave college. I don't think anyone ever does that anymore. Don't drink and derive.
Oh, that's the best engineering joke I think I've heard all year. Don't drink and derive. You heard it here, folks, on the Being an Engineer podcast from Shawn Patterson.
Correct.
I think that's a really good point you make about learning how to think. And I'm not sure I've ever thought about it that way. So that was insightful for me to hear. I know for sure that one of the most important things I took away from my college education was learning how to think critically, analytically. But I don't know that I ever thought about, okay, exactly how did I learn that? And I think you make a really good point that it's like, doing the math problems, the physics problems, the fluid dynamics problems. It's yeah, you might use that someday, maybe. Shocker, I have not, like, ever really. But going through that process over and over and over does teach you how to think analytically. And I think that's one of the huge benefits of being an engineer.
It is. You use it hopefully in all aspects of your life because it is a tool and it's a powerful tool.
Yeah. All right. Well, this has been delightful, Shawn. How can people get in touch with you?
I can be emailed at engineeringssolutionsbysp@gmail.com. SP for Shawn Patterson. And you can find me on LinkedIn. I am Shawn Patrick Patterson, or I use my middle name. I'm on LinkedIn. I'm active on LinkedIn. I love reading articles there. And so, yeah, they can find me there.
Terrific. All right.
And my musicianship, that's a kind of a different angle but I use engineering and writing songs and audio engineering software for recording and sound, microphones, equipment, electronics. It all comes into play. Audio interface for your computers to produce music. So I can also be reached at the music style I make is called rustic rock music. And my website is called rusticrockmusic.com. And that's just that's the other side of me, is the musician, songwriter, acoustic guitar player, harmonica, singer. I really enjoy that a lot. So, I have a home life with my wife. I make music. She's my editor for music, and she helps me really develop my ideas. And then I love engineering.
That's awesome. And you're on Spotify as a musician as well, is
yes,
that right?
I use my mother's maiden name, which is Sinohui. So it's Sinohui, but I use my first name, Shawn. So Shawn Sinohui on Spotify, Apple, iTunes, everywhere that you can stream music, you'll find about 7 or 8 of my songs.
Terrific. Great. Well, I hope you get some new listeners.
That would be wonderful.
And thank you so much, Shawn, for being on the show today. What a pleasure it was to talk with you.
Great. I had a really great time, Aaron.
I'm Aaron Monker, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing turnkey equipment, custom fixtures, and automated machines, and with product design, visit us at teampipeline.us. Thanks for listening.